Hey everyone, welcome back. Today we're going to tackle a really fantastic coding problem. And what's cool about this one is that it's a perfect way to show off some truly powerful problem-solving patterns. So get ready, because we're about to crack the heaters problem.
The setup is actually pretty simple, but it's really elegant. Winter is coming, so imagine you've got a bunch of houses scattered along a line, and you only have a few heaters. Our mission, figure out how to set these heaters so that every single house stays warm. So here's our game plan for today. First, we'll break down exactly what the problem is asking. Then we're going to visualize it, really build up our intuition. This is going to lead us to a huge aha moment, which then opens the door to two super powerful strategies for solving it. And finally, we'll wrap up by adding these new patterns to your algorithmic toolkit. Sound good? Let's get started.
All right, let's dive right in. First things first, what is the actual goal here? What are we trying to find?
Okay, so here's the key thing you've got to understand. We're looking for one single radius value. It's not like each heater gets its own custom setting. Nope. Every single heater has to have the exact same warming radius. And our job, our whole mission, is to find the absolute smallest number for that radius that still covers every single house, not one left out in the cold. Now, before we even think about writing a single line of code, the absolute best way to get a feel for a problem like this is to just draw it out. Let's see it in action. We're going to build up our intuition with a really simple example. So just imagine a number line, right? Simple. We've got houses at positions 1, 2, 3, and 4. And we've got two heaters to work with. One's at position 1, and the other is all the way over at position 4. Okay, so looking at this picture, what do you think? What's the smallest possible radius we can give to both of those heaters to guarantee that every single house is covered? Just take a second and think about it. All right, let's walk through this together. The houses at positions 1 and 4, they're easy. They're sitting right on top of a heater, so they're already warm. They need a radius of 0. But what about the house at position 2? Well, its closest heater is at 1. So to reach it, we need a radius of at least 1, right? The distance is 1. Now look at the house at position 3. Its closest heater is at 4. The distance is, again, it's 1, so it also needs a radius of at least 1. And this is the key. To make sure everybody is warm, our one-size-fits-all radius has to be big enough for the house that's the most demanding, the one that needs the biggest radius.
And there you have it. The biggest of all those minimums we just calculated is 1. So for this setup, the minimum required radius is exactly 1.
And just by doing that simple little example, we've actually stumbled upon the core logic for the entire problem. This right here, this is our aha moment.
So listen to this, because this is everything. The required radius is just the maximum of all the minimum distances. Let me say that again. For each house, you find its closest heater, and that distance. You get a list of all those distances, and your final answer is just the biggest number on that list. That's it. That's the whole game.
Okay, so how do we actually turn that insight into an algorithm? Well, our first strategy is a little bit backwards, but it is so powerful. Instead of calculating the answer, we're actually going to guess it.
Yeah, seriously. Think about it like a guessing game. What if I could just test a radius? Like, I could ask, hey, does a radius of 5 work? And you could tell me either, yep, that covers everyone, or nope, not big enough. If we can build a function that just answers that simple yes or no question, then we can unlock a really, really cool technique. So how would this check function actually work? Well, the first thing we do is sort both the houses and the heaters. That's key. Then we can use 2 pointers, one for the houses and one for the heaters, and just kind of walk down the number line. For each house, we just need to see if it's within range of the current heater we're looking at. If it is, awesome. We move on to the next house. If the house is too far away, no problem. We'll try the next heater. We just keep doing this, and if we manage to cover all the houses, our check passes, our guess was good. Okay, so now that we have this amazing check function, we can unleash the full power of binary search. We start with a massive range of possible answers, say from 0 to 1 billion. We pick the number right in the middle and we check it. If it works, great. We know the real answer has to be that number or something smaller, so we can throw away the entire top half of our range. If it doesn't work, well, we know our radius needs to be bigger, so we throw away the bottom half. We just keep doing this, cutting our search space in half every single time until we zero in on that one perfect, smallest possible radius. All right, now for our second strategy. This one is way more direct. It follows our aha moment from the beginning almost exactly. We're literally just going to go house by house and figure out what it needs. So here's the plan for this one. Step 1, you guessed it, sort the heaters. This makes finding the closest one way faster. Then, for every single house, we find its nearest heater. We can do this really efficiently with another binary search or even 2 pointers. We calculate that distance, and we just keep track of the biggest distance we've found so far. Once we've gone through every house, that maximum distance we've been tracking, that's our answer.
So let's just put these two side by side for a second, because it's really interesting. The perfect guess method, it searches the answer space. It's asking a huge system-wide question: does radius R work for everybody? On the other hand, the house-by-house method searches the heaters array for each house. It asks a much smaller, local question: what's the closest heater to this one specific house? It's a really cool difference, right? One is an indirect, powerful pattern, and the other is a direct simulation of our core insight.
Okay, so let's zoom out for a minute. What are the big takeaways here? What are the key things you should be adding to your own algorithmic toolkit after seeing this?
Well, the number one most important first step for both solutions was what? Sorting. You absolutely have to remember this. Sorting often brings structure to a messy problem, and it's almost always the key that unlocks an efficient solution. Never, ever underestimate the power of a good sort.
And that brings us to the 2 big patterns to remember. First, binary search on the answer. This pattern is a total game changer. Anytime you're looking for a value and you can't calculate it directly, but you can check if a guess is valid, think binary search. And second, the 2 pointers technique. It's just an incredibly efficient, almost magical way to work with sorted arrays to find relationships between things. So I'm going to leave you with this one powerful question to take with you. The next time you're staring down a problem and you just can't figure out how to calculate the answer directly, stop and ask yourself this. Okay, forget calculating it. Can I check an answer if someone gives it to me? Because if you can answer yes to that question, you might have just unlocked the door to a beautiful, elegant, and super fast binary search solution.